clustering, which essentially assigns samples to a membership cluster. Since there's no label assigned for each sample, clustering is considered as an unsupervised learning. This can be accomplished in either hard clustering, which is called k-means, or soft clustering, which is done by using expectation maximization technique to estimate the latent parameters. So we're going to go through the module by following this outline. We're going to introduce the concept of unsupervised clustering by means of k-means, which is the hard clustering technique, and then get into the soft clustering, essentially to describe what the problem is by means of Gaussian mixture model. And then we're going to use EM, or introduce the concept of expectation maximization, as a way to estimate the parameters, the latent parameters, so that we can do the soft clustering. Okay, so just to recap what we've had so far in terms of both supervised and unsupervised learning. For supervised learning is to discover patterns in the data that relate to the labels, so that the patterns then are utilized to predict the values of the target labels for future data instances. For unsupervised learning, there is no associated, the data doesn't have an associated label. So this one is done essentially by looking into, say, similarities among the data set for performing clustering. Essentially, clustering is a technique for finding the similarity groups in data. For instance, it tries to group the data instances that are similar to or near each other in one cluster, as opposed to the data instances that are very, very different or far away from each other into different clusters. Clustering is also called unsupervised learning because there's no label values associated to each of these data instances. So due to the historical reasons, clustering is also often called or considered as synonymous with the unsupervised learning. So as an illustration, we can see that here in this two-dimensional plot of these samples, we can see that they're all unlabeled. There's no label associated to each of these samples. But with a visual inspection, we can see that there are three very natural clusters, because as you can see in this cluster, for example, any of the samples that belong to the cluster are situated very, very close to each other. Compared to, say, this one, using that as a reference, let's say this one here, also has its group of instances that are also very, very close to each other. And as well as, for example, the distance between these groups as clusters is also separated, because, once again, the similarity of this group, of the instances that belong to this group, are situated in the nearby samples in the same cluster. So there are many different uses for clustering, but essentially it is to group samples into clusters so that they can be better organized. For example, we can group people of similar size together to make, say, small, medium, or large, say, t-shirts. This is also good in marketing type of application. So, for example, we can actually segment different customer groups according to their similar interest. So In fact, clustering is one of the most utilized data mining technique because it is the clustering that would actually be very, very useful for the marketing purpose. So essentially, clustering, we can organize the clustering into two possible models. One is called the hard clustering, which is done by k-means. It's a clustering which is based on the distance of each sample or each instances to say k centroids. Whereas for the soft clustering, this is going to be explained or described in terms of Gaussian mixture model, where essentially we try to assign a probability to essentially to each of these samples, so that the sample does have the probability attribute information in term rather than being say binary, rather than say that this particular instance belongs to say certain cluster. It's going to say that it's going to identify that information in terms of probability. Okay, so let's talk about k-means, which, as I said, is a hard clustering technique. The way it is done by following these four steps. That is, we first of all decide on how many clusters that we're going to have. So that's going to then assign k objects as initial centroids. So that's where the k actually comes from. So we have to actually have that a priori information or decision so that this clustering is actually can take place. And then the next step is that each of the samples then are computed their distances to each of these k centroids. And then we're going to assign the samples to the cluster to which it is the closest. So this is the assignment step. And then after that, after every sample is decided on which centroids is the closest, then each of the sample then become assigned to that particular centroid. And then after that, we're going to compute new centroids for each cluster. So this is the new centroids step. And after that, we're going to repeat this process until convergence takes place. So that is the change in the centroids is going to stop if it is less than, say, selected convergence criterion. Otherwise, this is going to go to step one again, and this is going to be repeated. Okay, so let's take a look visually how this k-means algorithm is actually to take place. So once again, as a zeroth step by the samples, we initialize the cluster centers or centroids, and then we do the clustering. This is by means of assigning each of the samples to the k nearest centroids, and then determine the new cluster center. And then with that, it tries to modify until convergence takes place. So here's that step, the initialization. That is, we decide on how many centroids we're going to have. So let's just say that we want to have 3 centroids. So what we do is that we randomly select 3 samples, 3 instances, and say that they are the initial centroids. And then what we do is that we assign each of the samples to that particular centroid, which is in terms of the distance is the one that's having the closest distance. For example, you can calculate the distance between this centroid to this sample, and the same sample's distance is going to be calculated between here and here. And similarly, the same instance distance will be computed. So because this centroid is closest to, as far as this instance is concerned, we assigned this sample that belongs to, say, this particular centroid. So with that, we do that process for all of the samples. And as a result of the sample assignment to each of these three clusters, this is the result. Let's say these samples that are encircled by this belong to, say, M1, and those that are closest to M2 would be then be assigned to belong to M2, and those of the samples that belong to M3 would be encircled here. So this will be the cluster result by performing a distance measurement of each of the instances to the three initialized centroids. And then the next step is to modify or update the centroids by, for example, among those samples that belonged to, say, M1 centroid previously, then among these samples, it's going to recompute the new centroid. So before it used to be, the centroid used to be here. Now the new centroid, as a result of the computation for the centroid, would be right here. And similarly, we compute and update with a new centroid. So what's a centroid? Well, centroid is essentially the average value, right? Average value of the samples. So with that, then with the new centroids, then what you do is that we go through the update of the clustering. So by having this new centroids, what you do is that you then assign each of these samples to these new centroids. There could be, because of the updated say centroid, this particular one, for example, maybe a good example might be, let's just say that in terms of distance, they're not really, I mean, as clear at this point. But suppose that what used to be this one here used to belong to, say, M2. Now with the new centroids here, this belongs to, say, this, centroid. So the clustering is now updated, and this process then computes again and again for the computing the new centroids. So we do assign and then compute the centroids until the location of the centroids doesn't change very much. So this is when we say that the convergence has taken place. In other words, the change of the location or the centroid at M1 at, say, K step versus that of K plus 1 step or the next step, if the change is very, very small, then we say that the convergence has taken place. Okay, just to show you in a little bit more, zooming into the process. So here's another example. So suppose we have an input data like this. So obviously each of these samples, instances, there's no label associated. But what we do is look for the similarity. And this is how we're going to do the clustering. So here what we do is that we randomly assign the centroids. And let's just say that here we need to initialize the centroids by deciding on how many centroids we're going to have. So we need to say that we have, say, 2 centroids. So let's just say that k is equal to 2. So with that, we randomly select 2 instances and say that they are the centroids, the initial centroids. And with that, what we do is that we assign, right? We assign each of the instances of the samples in terms of the distance. So for example, for this centroid, the one that's closest would be this. So this one is assigned to this. Whereas for this as the centroid, the one that's compared to, say, this guy here to this one is shorter, so this belongs to this. And similarly, this one compared to this distance to this one is shorter, so this also belongs to this. So we can assign these 3 samples that belong to this centroid. And then with that, we can then compute the new centroids. And the new centroids, because these 2 samples initially belong to the same cluster, so out of the 2 cluster, what we do is that we take the average value of these 2, which therefore is going to give you the new centroid location being right here. And the average of these 1, 2, 3, 4 samples for this cluster would be right here. So we can then compute the new centroids. And with that, once again, we compute the distances to each of these samples again. So with this, say, new centroid being here, the samples that are closest happens to be this one, and also this one here. Because as you can see, that this one here, the distance to here, from the new centroid to here, compared to, say, this one to this distance, it's much shorter, right? This is much shorter. So therefore, so we can say that this belongs to, say, this new cluster. And similarly, these 3 samples belong to this. So we now have accomplished assignment to the new centroids. And then at this point, what we do is, once again, we compute the new centroids, right? So the new centroid of having these 3 samples, the new centroid happens to be right here. So this is the new centroid, and then similarly, this cluster's new centroid happens to be right here. And so we kind of compute this assignment and updating the centroid and so forth, on and on, until, as you can see, that the centroid's location now doesn't seem to be changing very much. So this then becomes the converged centroids. So this is how k-means work, which seems to be rather pretty simple process. So this is actually an animation. So a new example, another example is that, so we randomly initialize the centroids. But before we do that, we need to decide on how many centroids we're going to have, or what the number of the cluster would be. So in this case, let's say k being, say, 2 or 3. And we're going to repeat this until there's no change in the centroids. So let's just say that k in this case would be 3. So we now have 3 randomly chosen instances and assign them as the initial centroids. And then once again, at that point, what we do is that we compute the distances of each of these instances to the centroids, and see which of the centroid is the closest, and assign that instance to that particular centroid. And after that, what we do is that we recompute the centroids. So this is the computation of the new centroids. So here, for example, among those samples that used to belong to the centroid being, say, here, now we recomputed the centroid, the new centroid being right here, and similarly, new centroid being here and here. So this process goes on and on. until once again the centroid doesn't change anymore. So we compute the centroids and we assign the samples to the closest center. So at this point, as you can see, the centroid doesn't seem to be changing very much. So this is when we say the convergence has taken place, and then say that the algorithm should stop. Now, k-means, however, has a weakness as far as outlier is concerned. For instance, suppose we have an outlier like this guy here, with the initial centroids being right here. What happens is that with the introduction, with the presence of this outlier, it's going to compute the centroids, one being here, another one being here, that belongs to this group. And because of this outlier, as you can see, this particular outlier has actually become separated away from the rest of the samples, even though the samples seem to be much better in terms of clustering if we separated the samples between this and this, right? But because of this outlier, turns out that we are separating or having the cluster as this outlier as one cluster, and the rest of the samples being another cluster. So this is the weakness, and the a big influence if there is an outlier as far as the location of the centroids. But nevertheless, it is much, as you can see, very simple process to proceed in terms of grouping different samples into clusters. Now, on the other hand, we are going to have very different situations when we wanted to model certain samples. For instance, like in the Gaussian mixture model. For example, what's a Gaussian mixture model? Suppose we have samples that are, well, here I have them colored, but let's say that we have these two set of the samples, clusters, pretty much separated, because the way that each of these samples instances are located, even though let's say they are not labeled. Say all the colors of the instances are black. This is going to be a good application for hard clustering because they are well separated themselves. On the other hand, we could also have situations like this, where, for example, you might have the samples that are sort of like laying on top of one another. So, for example, you may have, for example, two set of the clusters, not necessarily labeled, but let's just say that these samples that belong to this red circle are all in the same, say, class or same cluster, whereas all of the samples that belong to the blue belong to, say, another class. However, because of the fact that they are not labeled, as you can see, each of these samples could be overlaying on top of one another. So it's going to be very hard to say which of the instances belong to which cluster. As a matter of fact, the defining cluster of this, when you have these two clusters that lay on top of one another, is actually a very challenging problem. So instead of saying a hard cluster, like the way we've done with k-means, where, for example, which would be very good application for instances or samples that are pretty much linearly separated already. In this case, what we want to do is, instead of saying that the sample belongs to, say, cluster 1 or cluster 2, we could say is that the sample belongs to, or the probability of the sample that belongs to, is certain. Rather than saying like a hard clusters decision, what we could do is to assign each of the sample with a probability. So that's what is meant by soft clustering. And this is going to be certainly good, especially when you have a Gaussian mixture model situation. So what's a Gaussian mixture model situation? So for instance, like you could have a simple Gaussian case. For example, this is a say some population instance of say Seoul to that of the Jeju, and for Seoul group, let's say the population's probability distribution looks like this, which is Gaussian, and then Jeju has a probability density distribution looking like that. So this is a unimotor Gaussian. So in this case, it's a we say that as a simple Gaussian case. On the other hand, if the distribution consists of two or more Gaussians, like for example, like in the case of say Sahara, so Sahara has two modes like this. We say that it's got this is a multimodal situation, and say that it's a mixture model. In this case, we cannot actually compute the parameter using the single Gaussian case model. So this is where that mixture model comes in when you have a multi-modal situation. If that's the case, then how do we then describe this mixture model case in terms of the modeling? The way we're going to model it is going to be called Gaussian mixture model, which is a linear combination of the or sum of the linear combination of the unimodal Gaussian, where unimodal Gaussian has its own, let's say, parameters. Let's say this one here, say ith Gaussian might have its own mean or the center, as well as the the variance or the covariance. And similarly, this one has its own center, where the center location is say mu2, and this one here, the center location would be mu1, and also the variance, right, or the covariance. Let's say that this is say sigma 2, and this one here is sigma 1. So you could define the mixture model having multimodal Gaussian situation looking like that, which is going to be like this, as a sum of the combination of each of these unimodal Gaussian, where each of the unimodal Gaussian is represented by two parameters, the corresponding two parameters. One in this case would be the mu, say mu, as well as say covariance. And how they're weighted is going to be represented by this prior probability or weight probability. So you could have samples that are distributed in this mixture Gaussian model type. So this one here, the Gaussian mixture model, is very much parametric in the sense that you can define this mixture Gaussian model by means of these parameters. What are the parameters? First of all, it's got the mean and the covariance for each of these Gaussian, and we have also P of say phi sub I, which represents the weight. So these are the information or the parameters that could be, if we do have that information, that can define a certain multimodal mixture model case like this. Now, however, to be able to actually model this, then we have these samples, and the samples that need to be assigned to represent which of the cluster or the Gaussian that this sample belongs. And the way it is going to be done is by means of expectation maximization procedure. So this is going to be also considered as an unsupervised learning because there's no samples with labels. Not only each of the sample that's used to model this Gaussian mixture model is that they don't have any labels. As a matter of fact, they don't have any parameters as of yet. These are considered as latent variable, which needs to be estimated. Which needs to be estimated by means of the maximum likelihood estimation, which that procedure is called expectation maximization procedure. Okay, so just to recap what we have done is that we need to understand how the data set is being produced for, let's say, once again, for the purpose of clustering. So before we have mentioned about hard clustering process, where given an unlabeled data by assigning, say, centroids, that we could actually form, say, cluster. So that would be considered as hard clustering technique, or k-means clustering. Whereas here in this case, the way how these samples are produced or generated is by means of this process, by using, first of all, this weight procedure. So this module here, this block, essentially tries to choose, in order to generate a particular sample, that this module will try to randomly select which of the Gaussian model that this sample is going to be to belong. So that's going to be done in terms of, that's going to be represented in terms of the probability. So this probability assigns which of the Gaussian model that this particular sample belongs. Let's say that it chooses probability to be this, or having certain probability. Then this G2 will then have the sample which is generated according to the likelihood, which is described by this module G. So that would be, once again, it's sort of like saying that it's the likelihood of the probability being generated by, let's say, this particular model. Let's just say that that would be omega sub I. Okay, so this is what that is, and then this probability is a single Gaussian model, right? A single mode Gaussian model. So this is how we assume that the data points are generated. So each of these data points are generated that way. So assuming, let's say, because as you can see by inspection, seems like that it would be good to have just a two Gaussian mode, two clusters, essentially two big clusters. So we can have, say, G1 and G2. So each of these samples that are generated, this is 2D and this is 1D. So let's just say, let's assume that we have a 1D situation. So each of these samples that are being generated, which is like this, right, here on the horizontal axis. What we want to do is to say that these samples are generated according to, once again, having this P of phi sub I, which is the random number generator probability, where this essentially what it does, that it chooses which of the two Gaussian mode that the sample comes from. So therefore, once again, each of the sample then, what we want to do is to essentially represent the samples belonging to which of the two Gaussian that it belongs in terms of its posterior probability. So for example, omega say 1 given say x. So this is what we want to do, is to assign each of the samples and compute its posterior probability. And to be able to then obtain the posterior probability, what we need to do then is to be able to compute the probability of the sample that came from say either G1 or G2, which is called a likelihood. So mixture model is obtained by this unsupervised learning, where we try to assign the sample with this posterior probability. Rather than saying that belongs to G1 or G2, we say that what is the probability that this sample belongs to, and we try to describe it in terms of probability. Okay, so then question is, how do we estimate the model parameters? So the model parameter that can be estimated is going to be done by a maximum likelihood estimation procedure, which is done by maximizing the likelihood with respect to the parameter. So in other words, what is the parameter that maximizes this likelihood? That's what the maximum likelihood solution is. And for a simple Gaussian model that is having just a single Gaussian like this, single mode, then what you do is, after obtaining the likelihood function representation, and you take the natural log, and then what you do is that you take the gradient of that with respect to theta, and then set that equal to 0, and then solve for the parameter theta. So this is going to be good, once again, if you have a simple case like this that is having a single mode, a Gaussian case. So the solution as a result of this MLE process is going to be essentially a sample mean for the location of the mu, and then the sample covariance. So this is the, say, sample covariance would be this. So these two can be estimated as long as you have this single Gaussian case. On the other hand, for the mixture density case like this, having a multimodal situation, the solving MLE is no longer possible, because we're going to have multiple number of maxima on the likelihood function. That is, suppose you have this likelihood function representation which is multimodal, and if we take the natural log and then take the gradient of it, we are going to certainly have multimodal situations like this, meaning that if we cannot actually tell if, because there's only one say mu in the case of estimation of the parameter, it's going to be one, either this or this. We cannot really decide on which one is which, because we have a multi-modal situation. In other words, here in this case, we need to have two, right? Two means to locate this and this. But the MLE solution with the gradient of the log of p, x, and theta, and set that equal to 0 is going to just produce with a single parameter, just one parameter. So we cannot obtain the parameter values by just going through the MLE as is. So so to remedy this situation, to mitigate this problem, the solution of the Gaussian mixture model is done by means of the expectation maximization algorithm. So what's expectation maximization algorithm? It's an algorithm which is to find the maximum likelihood estimate of the parameters when the data has some missing values or latent variables. It's the same thing actually, latent or missing. Or hidden is another way of describing, or hidden variables. Latent or hidden or missing values, they're all the same. What's the notion of this latent variable or hidden variables? We say that we have an incomplete data because certain structure of the data set as they are generated are essentially hidden. For example, the only thing we can do is in terms of the samples is that we can observe the samples, but we cannot observe the inherent structure, the internal structure that generated the data. So we say that those of these hidden structure as the unobserved data or missing data. Well, we have not actually talked about hidden Markov model yet. So for the hidden Markov model, it would be say those of the sequences of the state would be an example of the hidden variable for hidden Markov model, which, by the way, we're going to talk about that at the next round of module. In the case of GMM, the Gaussian mixture model case, it would be the Gaussian components. In other words, we talked about, say, remember how each of the samples would be represented. It was done by, say, P. It was done by having, say, P of phi sub I, right? So this is one hidden information, and then we have the mu as well as the covariance. So these are the parameters which essentially are hidden, and we don't really have that information. Because of that, because each of the sample, say x of I, doesn't have that which of the Gaussian that it came from, that's exactly the information that we are trying to model and then estimate by means of this expectation maximization. So in order to have a complete data, then we are going to not just have the data here, but also as well as these data or these data that's going to make up so that Z becomes complete. So the Y, the missing data, in the case of the Gaussian mixture model would be this as well as this. So to define a complete data, we can do so in terms of likelihood. So the complete data likelihood would be, once again, the samples that are observed plus those of the data set or the structure, which is defined by, say, Y. So combination of the two, X and Y, would be then equal to Z. So Z would be, say, here the Z would be both, as you can see, Xi, so I should say X and Y together as a joint probability. And because once again, since Z is a complete if you do have both X and Y, but because Y is hidden, we can say that the probability of Z given the parameter is actually a random variable because Y here is unknown or have not decided. In other words, each of the sample it doesn't really doesn't have the information of which of the cluster or Gaussian that it belongs. So that's exactly what we want to do, is to establish that, which is going to be done by expectation maximization. So we're going to show you a couple of examples from very simple examples of maximum likelihood estimation, as well as for the case of the Gaussian mixture model of obtaining those parameters by means of expectation maximization operation. So before we talk about that, let's talk about the maximum likelihood estimation procedure first. We say that first of all, we need to obtain the log likelihood of the log likelihood of the sample, and then we take the gradient of that and, with respect to the parameter and set it equal to 0, and then solve for the parameters. So what that actually means is that the maximum likelihood solution essentially seeks the solution that best explains the data set. In other words, what is the solution that best explains the data set? So these are the samples that are that are generated. So the solution that best describes or explains the data set would be for a univariate or single mode Gaussian distribution case, would be represented by the mean and the variance that best describes the data set. So each of the sample, let's assume that it can be modeled with a single Gaussian distribution case, where the single Gaussian distribution case would be essentially this. So from the sampled data, and assuming that you have mean and the variance as the parameters, these are the parameters that is described by the samples. Then what you do is that you essentially go through the natural log, taking the natural log of the likelihood once again, and then take the gradient of it with respect to theta, or the parameter, and set that equal to 0, and then solve for the parameter. Essentially, then what you do then in the case of the samples, as described by a univariate Gaussian, you are going to then have these two parameters estimated, essentially the mean as well as the covariance or the variance. So for the 1D case, it's going to be the mean as well as the variance. For a, say, 2D or multi-dimensional case, it's going to be essentially mu will be a vector, and the spread of the data is going to be represented by the covariance. So how do we take the maximum likelihood? Once again, what you do is that you take the likelihood function of the samples, assuming that this is Gaussian with these two parameters, mu and, say, variance, or the mean and the variance, where each of the samples are assumed to be independent of each other. So therefore, for n number of the samples, you can say that the joint probability of the likelihood for, say, all of the samples can be described by essentially a product of these individual marginal probability for each of the samples. And then what you do is that you then put a natural log on the likelihood, and then with that, so the natural log of that would be actually give you this, and what you then do is you take the gradient or take the derivative and set that equal to 0. That's what the derivative is, right? And we do that for two parameters, one for the mu and one for the variance. For the case of the variance, in the case of the mean or the mu, so that would be the MLE of mean. So you take the gradient or the partial derivative of this log likelihood and then with respect to the mu and set that equal to 0. And so when you do that, this is the log likelihood. And then you take the partial derivative of that with respect to mu and set that equal to 0. And then you solve for the mu. So mu is going to be essentially, as you can see, sample mean, which is essentially expected. And similarly, you can do that for the variance for one dimension or covariance for a multi-dimension, right? So we go through exactly the same process. So we take the natural log of the likelihood and then take the partial derivative of this log likelihood with respect to the variance and set that equal to 0. And then we solve for the variance or covariance. In the case of, let's say, one-dimensional samples, let's just say, assume that it's going to be one-dimensional sample, so that it's going to be variance. So the variance is going to be equal to this, where, as you can see, that the first term represents having to do with the values of the samples, and the second term here is having to do with the, as you can see, the sample mean, which is computed by taking the MLE of the mean as shown by the previous slide. Okay, so let's then proceed with obtaining a expectation maximization procedure for a simple scenario, and that scenario is that we're going to assume in this scenario that there are some missing data. So in the case of the missing data, remember that we are going to be doing the sampling, where the sampling we have n number of the samples, where, however, that we have up to m numbers as shown as being available, whereas all of those samples from m plus 1 to n, we know that there are samples, but we don't have the values. Okay, so we can say that these samples have the missing data situation. So Z is a complete data set, where the complete data set then would be combination of both those of the samples that have the values present, as well as those of the samples that does not have the values or the missing data. So in this case, what we want to do is that we're going to go through the expectation maximization procedure to obtain and estimate the parameters. So that is we want to estimate the parameter by using the maximum likelihood estimation by means of the EM procedure, expectation maximization. So once again, what is that we're trying to do? We're trying to estimate the parameters. So before we could be, let's just say that we have this many. Let's say we have this many samples for obtaining, say, the mean. But we also have let's say, the samples that are also missing in values. So we have let's say, 5 more or 4 more, or let's say 5 more samples, but we don't know exactly the position of these samples. So with that, what we want to do is, once again, by going through the expectation maximization, what we want to do is to establish where that mean, where that location of the estimated parameter for, in this case, let's just say that the mean value would be. So the mean value, as you can see, is a sample mean, and it's going to require all of the values from, say, n from 1 to, say, I from 1 to, say, n samples, right? However, we only have sample values up to m, and the rest it is missing. So this one here is missing. And similarly for the computation of the variance or the estimate of the variance, these values are missing. So that's going to be problematic for now, right? How do we then estimate the mu when these values are going to be missing? Well, the procedure that we're going to be using is called expectation maximization, which is an iterative process using a two-step approach. First step would be the expectation step, and then the second step would be the maximization step. So expectation is essentially taking the expectation or averaging over all the parameters. So for example, and before we do that, by the way, the expectation procedure is going to require some initial values. So it's going to we need to assume some initial values to start off. And then obtain and then estimate the parameters. So how do we estimate the parameters? The estimating the parameters would be, for example, remember we said that the computation or the estimation of the mean would be this, essentially. So whereas the first term has the values, and the second term we don't have the values. And similarly for the variance, we have the first term having values, and the second term we don't have the values. Although this one here actually comes from the estimated mean. Now, if you can think about this, how do we then estimate this part, the unknown, the missing part? That missing part can be done by essentially an estimation, and that estimation is essentially to multiply, say, let's say that suppose that the mean happens to be known. Okay, assuming that the mean is known, then we can multiply the mean times that number of index that overlaps with the missing say samples. So that would be n minus m. So n minus m is multiplied by let's say an assumed mean, which is going to be this. That assumed mean is the initially assumed, say, parameter value. That is, we can essentially estimate this value here, the sum of all these missing values, to be as the product of, let's say, the mean times those of the samples that belong to the missing values, which would be n minus m. Now that's going to require this mean or the information over the mean, but the information of the mean we're going to start off with some initial value, some initialized value. So this is how we can compute the missing value to start off, and similarly we can do that for the let's say computing say sum of the squares. So that's going to be done by, once again, those segment n minus m and multiplied by, say, the square of the assumed mean plus say the assumed or initialized variance. So here, once again, we're assuming that we know this information as well as this information to start off. So with that, we can then have a temporary sum for the iterative process as follows. That is, for the sum of all the samples would be those of the samples that has the values plus those of the samples that are missing. So this term here would represent those of the missing samples. And similarly, we have for the variance computation. This one represents those of the samples that has values, whereas this term represents those of the missing samples. And then the next step is we say that as a maximization step. This is is to update the parameter value for the next iteration step, which is obtained by the estimation. And that estimation is, for example, for the mu, it's going to be the sum of all the values, those of the values that has the values, those of the samples that have the values, and as well as those of the samples that are missing, to be divided by the total number of samples, which happens to be, say, n. And similarly, we can do the same for the variance computation. So that would be, say, all of the total values of the sum of the squares, including those of the missing values, and we divide by n. And then it is going to be subtracted off by, say, this, where, because we saw that if you go back to the computation of the sigma square, or the variance, let's just go back. We had that to be this. So this is actually subtracted. So as a matter of fact, so we do this E step and then the M step, and then we go back, repeat this process until these values actually become converged. That is, they don't really change anymore. So here's a numerical example, which I have just as an illustration. So I have a just sequence of these values. There are, I think, about 18 numbers, where if we have all the values that are revealed, then the mean in this case would be 3.91. Now, suppose we have these values being, say, unknown or missing. So I'm going to just put them as, let's say, missing, or A. And based on this expectation maximization procedure, which I just did, that is by using, say, initially with some assumption, and I'm going to assume initially that the mean would be, say, 8, the mean of the entire 18 numbers would be 8. And then after going through the EM procedure for about 10 times, then it's going to essentially converge to 3.83, which is very, very close to the true mean, which happens to account for these values. So this means, and similarly, I've done that with, let's say, initial value being, say, starting off with 4, and once again, going through this iterative process, going back and forth the expectation and maximization, the number converged to be 3.83, which is also very close to the true value. So expectation maximization procedure seems to work, as at least on the missing data situation. Okay, so this is going to then